There's a place in the universe where the rules we take for granted, gravity, time, even the fabric of space itself, utterly collapse. A place so dense, so powerful, that not even light can escape its grip. This isn't science fiction. This is the reality of a black hole. And today, we're going to venture where few minds have dared to go, peeling back the layers of one of nature's most profound mysteries. What really lies inside a black hole? Is it a gateway to another dimension, a crushing singularity, or something beyond our wildest imagination? The answers might just redefine everything we thought we knew about the cosmos. Think about the sheer scale of it for a moment. A single black hole can weigh millions, even billions of times more than our sun, yet it's compressed into a space smaller than a pinpoint. The forces at play here are so extreme that they warp the very fabric of reality, bending time like a piece of rubber and stretching space into a cosmic funhouse mirror. And here's the thing, we've never actually seen what's inside. No probe, no telescope, no human invention could survive the journey. So how do we even begin to unravel this enigma? That's where the magic of science comes in. Through brilliant theories, groundbreaking simulations, and clues hidden in the ripples of spacetime, we're piecing together a picture of the unimaginable. This isn't just a story about distant cosmic oddities. It's about the limits of human curiosity. Black holes challenge us to think bigger, to question deeper, and to confront the edges of our understanding. They remind us that the universe is far stranger, far more magnificent than we could ever dream. And as we dive into the latest research, the boldest ideas, and the mind-bending possibilities, you'll start to see why scientists call black holes the ultimate laboratories of physics. So if you've ever stared up at the night sky and wondered what secrets it holds, you're in the right place. Because by the end of this journey, you won't just know what's inside a black hole, you'll feel the awe of standing at the threshold of the unknown. To grasp the staggering reality of a black hole, picture the final moments of a dying star, one far more massive than our sun. When such a star exhausts its nuclear fuel, the outward pressure that once held it up vanishes, and gravity takes over with crushing force. The star collapses inward, compressing its entire mass into an infinitesimally small point called a singularity. Around this unfathomably dense core, spacetime bends so severely that it creates a boundary, the event horizon, a one-way door where anything that crosses, from stardust to light itself, can never return. But here's where it gets even stranger. The event horizon isn't a physical surface. It's more like a mathematical line of no escape. Think of it as the universe's ultimate prison wall, but instead of bricks, it's woven from gravity's invisible threads. And once you're inside, spacetime isn't just bent, it's shattered. The laws of physics as we know them cease to function, leaving scientists to rely on Einstein's equations to glimpse what might lie beyond. General relativity tells us that space and time swap roles here. Forward isn't toward the center, it's toward the inevitable. Time becomes a one-way river, dragging everything toward the singularity at the heart of the black hole. Yet even Einstein's groundbreaking theory hits its limits at this edge of understanding. Near the singularity, gravity becomes infinite, and the fabric of reality twists into something our current physics can't describe. Some theories suggest quantum effects might take over, warping spacetime into loops or tunnels. Others propose that black holes could be gateways to entirely new universes. But one thing's certain, beyond the event horizon, the universe as we know it ends. What replaces it remains one of science's greatest puzzles, a mystery written in the language of gravity, waiting to be decoded. Crossing the event horizon is like stepping through a cosmic trapdoor. There's no turning back, no second thoughts. From the outside, this boundary seems deceptively quiet, just an invisible sphere in space. But once you cross it, the universe as you know it ceases to exist. Time doesn't just slow down here, it warps beyond recognition. For someone watching from a safe distance, you'd appear to freeze in place, your image stretched and dimmed as the black hole's gravity bends the light escaping from you. Yet for you, the traveler, time marches forward relentlessly, pulling you toward the singularity at the center with terrifying speed. What makes the event horizon so unnerving is how it distorts reality itself. Imagine space isn't flat but more like a flowing river, and the black hole is a whirlpool dragging everything toward its center. The closer you get to the event horizon, the stronger the current becomes until even light, moving at the universe's speed limit, can't fight against it. This is why black holes appear black. No light escapes to reveal what's happening inside. But here's the twist: you wouldn't even notice crossing the event horizon. There's no dramatic flash, no sudden jolt, just the inexorable pull of gravity growing stronger with every passing moment. And then there's the tidal forces. A black hole doesn't just pull, it stretches. If you were falling feet first toward the singularity, the gravity at your feet would be so much stronger than at your head that your body would be pulled apart in a process scientists call spaghettification. It's as if the universe itself is playing tug of war with your atoms, elongating you into a thin strand before you even reach the center. This isn't science fiction, it's the brutal physics of extreme gravity. Yet amid all this chaos, the event horizon holds a strange kind of order. According to Einstein's theory, it's the point where space and time swap roles. Outside the horizon, you can move freely through space but must move forward in time. Inside, space becomes a one-way path toward the singularity, and time loses all meaning. It's as if the universe flips the rules upside down, leaving physicists grappling with questions that push the boundaries of human understanding. So what happens beyond this point of no return? The truth is, we don't know for sure. Some theories suggest the singularity is a place of infinite density, where all known physics breaks down. Others propose that black holes might be gateways to entirely different realms of reality. But one thing's certain: the event horizon isn't just a boundary, it's a frontier, the edge of everything we understand, and the beginning of a mystery that continues to captivate scientists and dreamers alike. Imagine being pulled into the strongest gravitational field in the universe, where the force at your feet is exponentially stronger than at your head. This isn't just a tug, it's a cosmic stretch so violent that it warps your very shape, elongating you like a piece of melting taffy. Scientists call this nightmare scenario spaghettification, and it's one of the most bizarre and brutal effects a black hole can inflict. The physics behind it is as simple as it is terrifying. Gravity weakens with distance, so if you're falling feet first toward a black hole, your lower body feels a far stronger pull than your upper half. The difference isn't gentle, it's extreme enough to overcome the molecular bonds holding you together. Your body stretches thinner and thinner, like dough being pulled apart, until you're nothing more than a stream of atoms spiraling toward the singularity. But here's the chilling part: you wouldn't just snap instantly. Depending on the black hole's size, the process could take seconds or even minutes, plenty of time to realize what's happening. Smaller black holes are actually more dangerous when it comes to spaghettification, because they pack their mass into a tighter space, the gravitational gradient. The difference in pull from one point to another is far steeper. A stellar mass black hole just a few miles wide would stretch you apart long before you reach the event horizon. Supermassive black holes, like the one at the center of our galaxy, are gentler in a macabre way. Their immense size means the tidal forces spread out over a larger area, so you might cross the event horizon before the stretching begins. But make no mistake, once you're inside, the end result is the same. This isn't just theoretical. Astronomers have observed spaghettification in action, not with unlucky astronauts but with stars. When a star wanders too close to a black hole, the tidal forces rip it apart in a spectacular event called a tidal disruption flare. The star's material doesn't just vanish, it's shredded into a glowing streamer that spirals into the black hole, heating up to millions of degrees and emitting X-rays we can detect across the universe. Yet even in this destruction, there's a strange kind of beauty. Spaghettification reveals the raw power of gravity, warping not just space and time but matter itself. It's a reminder that black holes aren't just cosmic vacuum cleaners, they're laboratories of extreme physics, where the universe tests the limits of reality. And as we study these violent transformations, we're learning more about how gravity shapes everything, from the tiniest particles to the largest structures in the cosmos. Deep within the black hole, past the event horizon and beyond the violent stretch of spaghettification, lies the most baffling mystery of all, the singularity. This isn't just the center, it's the point where reality itself unravels. Imagine taking the entire mass of a star, or even billions of stars, and crushing it into an infinitely small dot. No volume, no space, just pure, unfathomable density. Here, gravity doesn't just bend space-time, it shatters it, warping the fabric of the universe beyond recognition. But what does infinite density even mean? Our best theories, like Einstein's general relativity, predict that at the singularity, space-time curvature becomes so extreme that the equations spit out nonsensical answers, literally dividing by zero. It's as if the universe is handing us an error message, telling us our understanding of physics is incomplete. And that's the real puzzle. The singularity isn't just a place where matter is squeezed, it's where the rules of the cosmos as we know them cease to exist. This is where quantum mechanics and gravity collide literally. In the everyday world, gravity and quantum theory operate in separate realms, but at the singularity, they're forced to interact and the results are chaotic. Some scientists believe quantum effects might prevent true infinity, replacing the singularity with a fuzzy, vibrating ball of energy. Others propose wild ideas, like the singularity being a bridge to another universe or a tear in spacetime itself. The truth is, we're staring into a mathematical abyss, trying to decipher clues without a full rulebook. One thing's certain, the singularity defies intuition. If you could somehow survive the journey to the center, you wouldn't find a place, you'd find a breakdown of place. Time wouldn't flow, it would spiral. Directions would lose meaning. Even the concept of inside becomes meaningless when space is infinitely curved. It's like trying to map the edge of a shadow. The closer you look, the less solid it becomes. Yet this isn't just theoretical hand-waving. The singularity forces us to confront the limits of human knowledge. It's a cosmic reminder that the universe is stranger than we can imagine, and that every answer we uncover only leads to deeper questions. Whether it's a gateway, a flaw in our math, or something beyond our current comprehension, the singularity remains the ultimate enigma, a silent, infinitely dense whisper from the heart of darkness. At the heart of a black hole's mystery lies a battle between two pillars of modern physics, each brilliant in its own right, yet utterly incompatible when pushed to the extreme. Einstein's theory of general relativity paints the singularity as a point of infinite density where spacetime curves beyond repair, but quantum mechanics, the rulebook for the subatomic world, insists particles can't occupy the same space simultaneously. It's like watching two master painters try to finish the same canvas, one using broad, sweeping strokes of gravity, the other with the fine detail of quantum particles, and neither can agree on the final image. This isn't just academic disagreement, it's a cosmic wake-up call. For decades, physicists have known their theories are incomplete. Relativity excels at explaining the large-scale structure of the universe, galaxies, black holes, the bending of light. Quantum mechanics flawlessly predicts the behavior of atoms and particles, but at the singularity, where the immense meets the infinitesimal, both frameworks collapse. Relativity's equations explode into infinities, while quantum mechanics rebels against the idea of a zero-dimensional point. The universe, it seems, is hinting that we're missing a crucial piece of the puzzle. Some scientists believe the answer lies in quantum gravity, a theory that would marry these two worlds. Imagine if gravity, at its core, isn't a smooth curve in space-time but a dance of tiny, discrete packets of energy. In this view, the singularity might not be infinitely dense, but instead a roiling foam of quantum fluctuations, where space and time lose their familiar shapes. Others propose even wilder ideas, like string theory's extra dimensions or loop quantum gravity's woven spacetime. What's fascinating is that black holes, these destructive monsters of the cosmos, might actually be the key to unlocking these secrets. Think of it like this: black holes are nature's way of conducting extreme experiments we could never replicate on Earth. The conditions at the singularity, where gravity is strong, distances are tiny, and energies are unimaginably high, are the ultimate testing ground for new physics. Every time we push our theories to the brink, black holes reveal their cracks, showing us where our understanding falls short. And that's the real magic here. This clash isn't a dead end, it's a beacon. It tells us that somewhere beyond our current knowledge lies a deeper truth, a theory that can explain both the vast cosmos and the tiniest particles. Whether it's through holographic principles, wormholes, or something entirely unforeseen, the singularity isn't just a problem to solve. It's an invitation to rethink, to explore, and to discover what the universe has been hiding in plain sight. Stephen Hawking turned our understanding of black holes inside out with a revolutionary idea: they aren't eternal prisons after all. In a brilliant twist of quantum physics, he revealed that black holes can actually leak energy, slowly fading away over unimaginable timescales. This phenomenon, now called Hawking radiation, is like finding a hidden door in a fortress once thought impregnable. Here's how it works: empty space isn't truly empty. Quantum mechanics tells us that even in a vacuum, particles and antiparticles constantly flicker in and out of existence, borrowing energy from the universe before annihilating each other in a flash. But near a black hole's event horizon, something extraordinary happens. These particle pairs can be torn apart. One falls into the abyss while the other escapes, carrying energy away. To an outside observer, it looks like the black hole is radiating heat, losing mass bit by bit. It's as if the universe has found a way to balance the books, ensuring nothing, not even a black hole, lasts forever. The implications are staggering. A solitary black hole in the void, with no stars or gas to feed on, would gradually shrink, its event horizon tightening like a noose. Over trillions of years, it could vanish entirely in a final burst of radiation, a whisper of its former glory. But don't expect fireworks anytime soon. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate. For supermassive black holes, the timeline stretches into numbers so vast they defy comprehension. Yet Hawking radiation isn't just about endings, it's a bridge between worlds. This delicate interplay between gravity and quantum mechanics hints at a deeper connection between the very large and the very small. It suggests that black holes, those cosmic destroyers, might also be the key to unlocking quantum gravity, the holy grail of modern physics. and there's a haunting beauty to it all. Even in the darkest corners of the cosmos, where light itself is swallowed, the universe leaves a faint glow. Hawking radiation reminds us that nothing is absolute, that even the mightiest forces are bound by the subtle rules of quantum uncertainty. It's a testament to human curiosity that we can peer into the abyss and find not just terror but wonder. Black holes might seem like cosmic vacuums, swallowing everything without a trace, but they hide a secret. They follow rules eerily similar to the laws of thermodynamics. It's as if the universe has a hidden playbook, and black holes are reading from the same chapter as steam engines and melting ice. Take temperature, for example. We used to think black holes were cold, dead voids until Stephen Hawking showed they actually emit radiation and have a temperature, however faint. This isn't just a quirk, it's a clue that black holes aren't just gravitational monsters. They're dynamic, almost alive in a thermodynamic sense, with energy flowing in and out in ways we're only beginning to grasp. Then there's entropy, the measure of disorder in a system. At first glance, a black hole seems like the ultimate order, a singularity, a single point of infinite density. But in the 1970s, physicist Jacob Bekenstein made a startling claim. Black holes have entropy, and a lot of it. In fact, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This turns our everyday intuition upside down. Normally, entropy grows with volume. Think of gas molecules spreading in a room. But for black holes, the surface area is what matters, as if all the information about what fell in is somehow encoded on its boundary, like a cosmic hologram. This connection between black holes and thermodynamics isn't just a curious analogy. It suggests something profound. Gravity, quantum mechanics, and the very nature of information might be deeply intertwined. Imagine throwing a book into a black hole. According to classical physics, it's gone forever, information destroyed. But quantum mechanics insists information can't be lost. The resolution, the information might not vanish but could be scrambled and imprinted on the event horizon, like a scrambled message waiting to be decoded. This is the heart of the famous black hole information paradox, a puzzle that's forced physicists to rethink the foundations of reality. What's even wilder is that this dance between black holes and thermodynamics might hold the key to understanding entropy on a cosmic scale. Entropy tends to increase over time, driving the arrow of time forward. Black holes, with their immense entropy, could be the universe's way of maximizing disorder, playing a starring role in the ultimate fate of everything. Some theories even suggest that, given enough time, black holes could become the dominant source of entropy in the cosmos, shaping how the universe evolves over trillions of years. So why does this all matter? Because black holes aren't just destructive anomalies, they're cosmic laboratories, testing the limits of our theories and revealing hidden connections between the very large and the very small. Every time we uncover a new law they obey, it's like finding a piece of a grander puzzle, one that might explain how gravity and quantum mechanics fit together. And if there's one thing black holes teach us, it's that the universe loves to surprise us, turning what we thought were cold, dead voids into some of the most dynamic and enlightening objects in existence. The idea that information could vanish forever inside a black hole sends shivers down the spine of any physicist. According to quantum mechanics, the universe keeps perfect records. Every particle, every interaction leaves a trace. Even if you burn a book, the information in its pages isn't truly lost. It's just scrambled into heat and ash. But black holes, they don't just scramble. They swallow, and if Hawking radiation causes them to evaporate entirely, what happens to everything they've consumed? Does the information just disappear? This isn't just a philosophical puzzle, it's a direct clash between two fundamental theories of reality, and the stakes couldn't be higher. At the heart of the paradox is a battle of cosmic rulebooks. Quantum mechanics insists information must always be preserved, like an indestructible ledger of the universe. But general relativity paints black holes as ultimate erasers, crushing matter into a featureless singularity. For decades, physicists assumed these two ideas could coexist, that the information swallowed by a black hole was simply locked away, inaccessible but still technically there. Then Hawking dropped a bombshell. If black holes evaporate, that information might be genuinely lost. The universe, it seemed, had a glaring loophole in its own laws. Enter the holographic principle, one of the most mind-bending solutions to this puzzle. Imagine the event horizon isn't just a boundary but a cosmic hard drive, encoding every bit of information about what falls inside. Like a hologram where a three-dimensional image is stored on a flat surface, a black hole's interior might be entirely described by data on its surface. When particles cross the event horizon, their information isn't destroyed, it's imprinted there, scrambled into quantum noise. As the black hole evaporates, this data could slowly leak back out through Hawking radiation, like a message in a bottle washing ashore after eons at sea. But not everyone's convinced. Some theorists argue the information might escape via entirely different routes: wormholes, hidden dimensions, or even parallel universes. Others propose more radical ideas, like the notion that black holes don't fully evaporate but leave behind tiny remnants, each a frozen archive of everything they've ever consumed. The debate is so intense that physicists have placed literal bets on the outcome, with Stephen Hawking himself famously switching sides multiple times. What makes this more than just academic sparring is the startling realization that black holes might be teaching us about the nature of reality itself. If information truly is preserved even in the heart of a black hole, it suggests spacetime is far more resilient than we thought, woven from something deeper and more fundamental. It's as if the universe is whispering a secret. Destruction is an illusion. Nothing is ever truly lost, just transformed in ways we're only beginning to decipher. And that's the real magic of this paradox. It forces us to rethink not just black holes, but the very fabric of existence. Whether the answer lies in holograms, quantum threads, or something beyond our current imagination, one thing's clear: the universe is hiding its secrets in plain sight, and black holes are the perfect place to start looking. Picture a world where everything you see, the depth of a canyon, the curve of a planet, even the space between stars, is just an illusion, a cosmic mirage projected from a flat, two-dimensional surface. This isn't the plot of a sci-fi movie. It's the essence of the holographic principle, a theory so radical it could rewrite our understanding of reality itself. At its core, this idea suggests that black holes don't just trap matter. They encode it, storing every atom, every photon that crosses their event horizon as intricate data on a two-dimensional boundary. Like a hologram where a 3D image emerges from a flat sheet of light, the universe might be projecting its richness from a hidden, lower-dimensional blueprint. The spark for this idea came from an unexpected place: black hole thermodynamics. When physicist Jacob Bekenstein calculated the entropy of a black hole, he found it wasn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the information about what fell inside every star, every molecule wasn't crushed into oblivion, but smeared across the surface like ink on a cosmic parchment. This bizarre discovery led researchers like Gerard T. Hooft and Leonard Susskind to a staggering hypothesis. What if the entire universe operates this way? What if the 3D reality we experience is just a shadow cast by processes playing out on some distant, unimaginably vast 2D plane. Think of it like a movie screen. The images appear to have depth, movement, even texture, but in reality, they're just patterns of light projected from flat film. The holographic principle takes this analogy to the extreme, suggesting that space-time itself might be an emergent property, a kind of illusion generated by quantum interactions at the universe's edges. Even stranger, this isn't just philosophy. In 1997, physicist Juan Maldacena mathematically demonstrated that a higher dimensional universe with gravity could be perfectly mirrored by a lower dimensional one without it, a duality that's since become a cornerstone of theoretical physics. But how could this possibly work? Imagine the event horizon of a black hole as a vast, ultra-fine mesh, each pixel storing a tiny bit of information. According to the holographic principle, these pixels, each no larger than a Planck length, the smallest possible unit of space, hold all the data needed to reconstruct the black hole's interior. It's like compressing a library into the dots on a postage stamp, where every book, every word is preserved in microscopic detail. And if this holds true for black holes, why not for the cosmos? Some theorists argue that the observable universe might be a projection from a distant, two-dimensional shell surrounding us, with every event, every particle interaction encoded on its surface. This idea turns our intuition inside out. We're used to thinking of reality as built from the ground up, particles forming atoms, atoms forming molecules, and so on. But the holographic principle flips the script, suggesting that the true source code of the universe might exist at its boundaries, with our 3D experience merely a rendering of that deeper data. It's a concept that bridges black holes, quantum gravity, and the very nature of information, hinting that space and time might not be fundamental at all, just emergent phenomena, like waves on an ocean whose true nature lies beneath the surface. Of course, not everyone's convinced. Critics point out that while the math is elegant, tangible evidence remains elusive. How do you test whether the universe is a hologram? Some experiments, like the holometer at Fermilab, have searched for telltale fuzziness in space-time graininess that might betray its pixelated origins, but so far the results are inconclusive. Yet, even without proof, the holographic principle has already reshaped physics, offering new ways to tackle black hole paradoxes and the unification of quantum mechanics with gravity. What's truly exhilarating is the possibility that black holes, those voracious devourers of light, might be the key to seeing reality anew. By studying how they encode information, we're not just solving cosmic puzzles, we're peering behind the curtain of existence itself, asking whether the universe is far stranger, far more interconnected than we ever dared to dream. And if the holographic principle holds, it means every star, every galaxy, even you and I, might just be the universe's way of reading its own reflection in the mirror of spacetime. Could the crushing depths of a black hole hide a secret tunnel, a cosmic shortcut stitching the universe together? The idea isn't just science fiction. Hidden within Einstein's equations lies a tantalizing possibility: wormholes, hypothetical bridges through spacetime that could connect distant regions or even entirely different universes. Picture folding a sheet of paper so 2 points touch a wormhole would be like punching a hole straight through, turning a journey of billions of light years into a single step. But here's the catch: wormholes, if they exist at all, would be wildly unstable. According to general relativity, these spacetime tunnels would snap shut the instant they form unless propped open by something with negative energy, an exotic form of matter that defies gravity instead of obeying it. Think of it like trying to hold open a tunnel made of quicksand. Without something pushing back against the collapse, it vanishes in a blink, and that's the problem. Negative energy isn't just rare, it's barely more than a mathematical ghost. glimpsed fleetingly in quantum experiments, but nowhere near the scales needed to stabilize a wormhole. Yet the dream persists, and for good reason. Wormholes aren't just cosmic whimsy, they're a natural extension of the same physics that predicts black holes. In fact, some solutions to Einstein's equations suggest that every black hole might be paired with a white hole, spewing out matter somewhere else in the cosmos, with a wormhole threading the needle between them. It's a poetic idea, the ultimate devourer and the ultimate giver, linked by a hidden highway through spacetime. Even more intriguing is the quantum angle. At microscopic scales, spacetime might be frothing with tiny, fleeting wormholes, quantum foam, where tunnels flicker in and out of existence too quickly to be traversed. Some theories propose that with enough energy and control, these could be enlarged, creating stable passages. It's a long shot, but it hints that the universe might be more interconnected than we ever imagined. Of course, there are darker possibilities. If wormholes do exist, they might not be the serene gateways of sci-fi. Tidal forces, radiation, and the sheer violence of spacetime warping could render them unsurvivable. Or worse, what if traversing one rewrites your timeline or spits you into a universe with entirely different physical laws? The unknowns are as vast as the potential. But perhaps the most mind-bending thought is this: if wormholes can link distant places or even different universes, they might blur the line between science and philosophy. Are we looking at cosmic plumbing or something deeper? A hint that all of reality is woven together in ways we've yet to comprehend. For now, wormholes remain a dazzling what if, a reminder that the universe's strangest corners are still waiting to be explored. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes would be their cosmic opposites, relentless fountains spewing matter and energy back into the cosmos. Picture a black hole running in reverse, where instead of an event horizon trapping light forever, there's a boundary nothing can enter, only escape. These hypothetical objects aren't just science fiction. They emerge naturally from the same equations that predict black holes, as if Einstein's math contained a hidden symmetry waiting to be uncovered. The concept is as elegant as it is bizarre. In theory, a white hole would be the time-reversed twin of a black hole. Where a black hole singularity crushes matter into oblivion, a white hole singularity would violently expel it. Where a black hole's event horizon is a point of no return, a white hole's would be a point of no entry, a cosmic keep-out sign etched into spacetime itself. Even light couldn't cross inward, it would be blasted away like water hitting an invisible force field. But here's the twist: while black holes are thought to form from collapsing stars, white holes have no known origin story. They can't be created in the same way because matter can't be forced inside them to begin with. Some physicists speculate they might be the other end of black holes, connected by wormholes in a grand cosmic loop. Others suggest they could be remnants of a black hole's evaporation, popping into existence when Hawking radiation finally causes a black hole to wink out of existence. Or perhaps they're relics of the Big Bang, primordial anomalies left over from the birth of the universe. The catch: we've never seen one. White holes, if they exist at all, would be spectacularly unstable. Pouring energy into the universe without restraint, they'd likely burn out in a flash like a firework with no fuse. Some theories even argue that white holes violate the second law of thermodynamics, dumping order into the cosmos without any apparent source of entropy. Yet despite these hurdles, the idea persists not just as a mathematical curiosity, but as a tantalizing clue that our universe might be more symmetrical than it appears. What makes white holes more than just a physicist's thought experiment is how they challenge our assumptions about time and causality. If black holes warp time to a standstill, could white holes reverse it? Are they glimpses of a universe where cause and effect run backward, or simply mathematical ghosts hiding in Einstein's equations? For now, they remain one of cosmology's great what-ifs, a reminder that the universe's strangest secrets might still be waiting just beyond the edge of our telescopes. Most black holes we know about are born from the dramatic deaths of massive stars, but what if some existed long before the first stars even flickered to life? Imagine the universe in its earliest moments, a seething, dense soup of energy where space itself rippled with violent fluctuations. In that primordial chaos, tiny pockets of matter might have collapsed under their own gravity, forming black holes not much larger than an atom yet packing the mass of an entire mountain. These aren't the cosmic giants we're familiar with, they're relics of the Big Bang itself, and they might still be lurking in the shadows of our cosmos today. What makes primordial black holes so fascinating is how they defy our usual expectations. Unlike stellar black holes, which form from collapsing stars, these ancient objects could be virtually anywhere, drifting through interstellar space, hiding in the outskirts of galaxies, or even floating right through our solar system. Their size would make them nearly invisible, yet their gravity would betray their presence. Some could be as light as an asteroid, while others might rival the mass of a small moon. And if they exist in vast numbers, they could solve one of astronomy's greatest mysteries, the nature of dark matter. For decades, scientists have been searching for the invisible stuff that makes up most of the universe's mass. Particles like WIMP and actions have been leading candidates, but despite countless experiments, no one's found conclusive proof. Primordial black holes offer a tantalizing alternative. If enough of them formed in the early universe, their combined gravity could explain the missing mass that holds galaxies together. It's a radical idea, dark matter not as exotic particles, but as countless tiny black holes sprinkled across the cosmos like invisible breadcrumbs from the dawn of time. The hunt for these elusive objects is already underway. Astronomers scan for telltale flashes when a primordial black hole passes in front of a star, bending light in a phenomenon called microlensing. Others study the ripples in spacetime from gravitational waves, hoping to catch the faint echo of two ancient black holes merging. Even everyday technology plays a role. Some researchers suggest that if a primordial black hole struck Earth, it could leave behind traces in ancient rock formations or even in the layers of our planet's crust. Yet the mystery only deepens when we consider their origins. To form in the early universe, these black holes would have needed regions of space hundreds of times denser than average. Was this the result of quantum fluctuations frozen into reality during cosmic inflation? Or did some other exotic process, like phase transitions in the newborn universe, create pockets of extreme density? The answers could rewrite our understanding of cosmology, linking the tiniest scales of quantum mechanics to the vast structures we see in the cosmos today. Whether they're the missing dark matter or just cosmic oddities, primordial black holes remind us that the universe is full of surprises. They challenge us to look beyond the familiar, to consider that the answers we seek might be hidden in the most unexpected places, not in distant galaxies or particle colliders, but in the echoes of the Big Bang itself, waiting to be uncovered. At the heart of nearly every galaxy, including our own Milky Way, lies a monster, a supermassive black hole so immense it defies earthly scale. These cosmic behemoths aren't just larger than stellar black holes. They're in an entirely different league, with masses ranging from millions to billions of times that of our Sun. Take Sagittarius, a star, the quiet giant at the center of our galaxy. Though relatively tame now, its 4 million solar mass gravitational grip shapes the orbits of nearby stars, whipping them around at dizzying speeds like planets caught in a celestial whirlpool. But how did these titans come to exist? The puzzle begins with their sheer size. A typical stellar black hole forms when a massive star collapses, but even the largest stars can't explain the birth of something a billion times heavier. One leading theory suggests they grew from smaller, seed black holes in the early universe, gorging themselves on vast amounts of gas and dust during cosmic feeding frenzies. Picture a raindrop swelling into a hurricane. Over billions of years, relentless accretion could have ballooned these seeds into the giants we see today. Another possibility is even more dramatic. In the crowded cores of young galaxies, black holes might have merged repeatedly, stacking their masses like cosmic Legos until they reached staggering proportions. Computer simulations show that in the chaotic early universe, galaxies collided frequently, and their central black holes would have spiraled together, releasing ripples in space-time we now detect as gravitational waves. Some of these mergers could have produced intermediate black holes missing links in the evolutionary chain before they grew into the supermassive rulers we observe today. Yet there's a twist. Some supermassive black holes appear too big, too early. Astronomers have spotted quasars, bright disks of matter swirling around ancient black holes shining from when the universe was less than 1 billion years old. How did black holes grow so massive so quickly? One radical idea proposes direct collapse, that in the dense, hot soup of the early cosmos, massive gas clouds could have skipped the star stage entirely, collapsing straight into black holes hundreds of thousands of times the sun's mass. It's like planting a redwood seed and waking up to a full-grown tree overnight, a growth spurt that challenges our understanding of cosmic timelines. What's truly remarkable is how these giants shape their homes. A supermassive black hole isn't just a passive sinkhole, it's an engine of creation and destruction. When active, its accretion disk glows brighter than all the stars in its galaxy combined, blasting out radiation and winds that can ignite star formation or snuff it out entirely. Some even shoot jets of particles at near light speed, carving bubbles in intergalactic gas that stretch for millions of light years. These black holes don't just live in galaxies, they sculpt them, tying their growth to the evolution of the cosmos itself. And that's the real magic here. Supermassive black holes aren't just cosmic oddities, they're keystones in the architecture of the universe. By studying them, we're piecing together a story that spans billions of years, from the first flickers of light after the Big Bang to the grand spiral galaxies we see today. Whether they grew slowly or erupted into existence, one thing's clear: these silent giants hold the pen that's still writing the history of the cosmos. When matter spirals toward a black hole, it doesn't just vanish silently into the void, it puts on one of the most spectacular light shows in the cosmos. Picture a cosmic whirlpool where gas, dust, and even entire stars are pulled into orbit, circling faster and faster as they near the event horizon. But friction isn't just a slow drag here, it's a violent, high-energy dance. Particles collide at unimaginable speeds, heating up to millions of degrees and glowing with the fury of 1 billion suns. This is the accretion disk, a seething ring of superheated plasma that transforms a black hole from an invisible predator into a beacon visible across the universe. What makes these disks so extraordinary is their sheer efficiency. As matter falls inward, it doesn't go quietly. Up to 40% of its mass can be converted directly into energy through Einstein's famous equation, E equals mc squared. Compare that to the paltry 0.7% efficiency of nuclear fusion in stars, and you start to see why accretion disks outshine entire galaxies. The energy released isn't just heat, it's a torrent of X-rays, gamma rays, and light spanning the electromagnetic spectrum, creating some of the most luminous objects we've ever observed. Take quasars, for example. These dazzling cosmic lighthouses powered by supermassive black holes can outshine 1,000 Milky Ways from billions of light years away. Their brilliance comes from accretion disks operating at maximum capacity, devouring stars and gas at a rate that defies imagination, but even smaller black holes put on a show. In binary star systems, where a black hole siphons material from a companion star, the accretion disk glows with enough intensity to reveal its presence across interstellar distances. Yet these disks aren't just cosmic blowtorches, they're also laboratories for extreme physics. Magnetic fields, twisted by the disk's furious rotation, launch jets of particles at nearly the speed of light, punching through galaxies and sculpting the space between them. These jets can stretch for millions of light years, acting as cosmic particle accelerators that challenge our understanding of matter and energy. And within the disk itself, turbulence creates strange structures like spiral shocks and standing waves, phenomena we're only beginning to model with supercomputers. What's truly humbling is how much we still don't know. Accretion disks shouldn't be as bright as they are, according to classical physics. Their light curves flicker in ways that suggest hidden dynamics, perhaps turbulence we can't yet simulate, or magnetic reconnection events that dwarf anything in our solar system. Even the disk's shape defies simple explanation. Far from a flat pancake, new observations hint at warped, wobbling structures, bent by the black hole's spin like a vinyl record melting in the heat. This isn't just about understanding black holes, it's about decoding the universe's most energetic engines. Every flicker, every flare from an accretion disk carries clues about how matter behaves under conditions we could never replicate on Earth. They teach us how galaxies grow, how the cosmos redistributes energy, and perhaps even how the seeds of life itself might hitch rides on jets of plasma. So the next time you hear about a distant quasar, remember, you're not just looking at a black hole's lunch, you're witnessing the universe's way of turning destruction into light. Some black holes don't just consume, they also unleash. Imagine a cosmic cannon firing beams of supercharged plasma at nearly the speed of light, stretching farther than the distance between entire galaxies. These aren't science fiction, they're relativistic jets, some of the most energetic phenomena in the universe, and they're powered by the very same black holes that devour stars. What fuels these incredible jets? The answer lies in the chaos of the accretion disk. As matter spirals toward the event horizon, it doesn't just heat up, it generates monstrous magnetic fields, twisted into coils by the black hole's spin. Think of it like winding up a rubber band until it snaps, except here, the energy released is enough to hurl particles across the cosmos. These magnetic fields act as cosmic railguns, channeling plasma into narrow beams that blast outward from the black hole's poles, punching through space with unimaginable force. The scale is staggering. The jets from supermassive black holes can stretch for millions of light years, far beyond the boundaries of their host galaxies. One of the most famous, the jet from galaxy M87, spans at least 5,000 light years and glows brightly enough for us to capture its image with the Event Horizon telescope. But what's truly mind-bending is the speed particles in these jets rocket outward at 99% the speed of light, making them nature's ultimate particle accelerators. Yet the mystery deepens when we ask how they form. Not all black holes produce jets, and those that do often switch them on and off like cosmic faucets. The key seems to lie in the black hole's spin. A rapidly rotating black hole drags spacetime around it, creating a vortex that twists magnetic fields into a tightly wound spring. When this energy finally releases, it's like uncorking a bottle of champagne, except instead of bubbles, you get a geyser of plasma hot enough to outshine stars. These jets aren't just spectacular, they're cosmic sculptors, As they plow through intergalactic space, they carve out vast bubbles in the surrounding gas, heating it and preventing it from collapsing into new stars. In some cases, they can even regulate the growth of entire galaxy clusters, turning black holes into unexpected architects of the large-scale universe. And here's the wildest part: these jets might be the source of the highest energy particles in the universe, cosmic rays with energies millions of times greater than anything we can produce in particle colliders on Earth. But the real magic happens when we look closer. Inside these jets, particles are accelerated so efficiently that they challenge our understanding of physics. How can plasma stay so tightly focused over such vast distances? What keeps the beam from dissipating into the void? The answers might lie in shock waves and turbulence within the jet itself, creating natural particle traps that boost energy to extreme levels. It's as if the universe has built its own version of the Large Hadron Collider, but on a scale we can barely fathom. So the next time you gaze at an image of a distant galaxy with jets arcing into the darkness, remember, you're not just seeing a black hole's leftovers. You're witnessing one of the most powerful engines in existence, a natural particle accelerator that's been running since before Earth formed and will keep firing long after we're gone. And somewhere in those beams of plasma, the universe might be hiding secrets about energy, matter, and the very laws that hold reality together. Standing near a black hole's event horizon would be like stepping into a scene from a sci-fi movie, except the time-bending effects wouldn't require special effects. Einstein's theory of general relativity tells us that gravity doesn't just pull on objects, it warps time itself. The closer you get to a black hole's immense gravitational field, the slower time ticks for you compared to someone watching from a safe distance. Picture this: if you could hover just outside the event horizon for what feels like an hour, years, even decades might pass for everyone back on Earth. It's as if the universe has handed you a remote control for time, with gravity pressing the slow motion button. This phenomenon, called time dilation, isn't just theoretical. We've already observed it in action, though on a much smaller scale. GPS satellites orbiting Earth, for example, experience time slightly faster than we do on the ground because they're farther from Earth's gravitational pull. Engineers have to account for this difference about 40 microseconds per day, or your navigation apps would lead you miles off course. But near a black hole, the effect is magnified to extremes. A clock falling toward the event horizon would appear to tick slower and slower to an outside observer, eventually freezing entirely at the point of no return. What makes this so mind-bending is the asymmetry. For the person falling in, time feels normal. You wouldn't notice anything unusual until the tidal forces took over. But from the perspective of someone watching you from afar, your descent would stretch out like a film stuck on pause. This isn't just a quirk of perception, it's a fundamental property of space-time. Gravity doesn't just bend space, it stretches time like taffy, creating what physicists call gravitational time dilation. The implications are staggering. If you could somehow orbit a black hole without being torn apart, you'd return to a universe that had aged centuries without you. In a sense, black holes offer a one-way ticket to the future, a natural time machine, though with no return trip. Science fiction often plays with this idea, like in Interstellar, where astronauts on a planet near a black hole experience hours while decades pass elsewhere. But the reality is even stranger. The universe doesn't just slow time near a black hole, it fractures the very idea of now, forcing us to confront the unsettling truth that time is fluid, not fixed. Yet here's the twist: time dilation near a black hole isn't just a cosmic curiosity, it's a clue to the nature of reality. The way gravity warps time hints at a deeper connection between spacetime and energy, a relationship that might one day help us unify quantum mechanics and relativity. And while we may never harness black holes as time machines, they've already given us something priceless, a glimpse into the universe's most elusive secrets, written in the slow dance of time itself. The universe has a secret language, one written not in light or sound, but in the very fabric of space-time. When two black holes spiral toward each other in a deadly dance, they don't just collide silently. They send ripples racing outward at the speed of light, stretching and squeezing space itself like waves across a cosmic pond. These are gravitational waves, and their discovery didn't just confirm Einstein's century-old prediction. It handed humanity an entirely new way to explore the cosmos. Imagine trying to study the ocean by only looking at its surface. For centuries, that's essentially how we observed the universe, through light, from radio waves to X-rays. But gravitational waves let us listen to the cosmos, picking up vibrations from events too violent, too dark, or too distant to see. When the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected its first wave in 2015, the signal came from two black holes 30 times the mass of our Sun, merging over 1 billion light-years away. In less than a second, they converted 3 suns worth of mass into pure energy, shaking space-time hard enough for us to feel it across the eons. The genius of LIGO lies in its simplicity. Picture 2 4-kilometer long arms arranged in an L shape with lasers bouncing between mirrors at their ends. When a gravitational wave passes through, it subtly changes the length of one arm compared to the other, by less than 1,000th the width of a proton. That's like measuring the distance to Alpha Centauri down to the thickness of a human hair. This incredible precision has opened a window into events we could once only theorize about: colliding neutron stars, supernova, even echoes from the Big Bang itself. What makes these waves so revolutionary is how they reveal the unseen. Take black holes. Before LIGO, we could only study them indirectly by observing their effects on nearby stars or gas. Now we can hear their mergers directly, learning about their masses, spins, and even how they formed. Some pairs might have been born together in dense star clusters, while others could be ancient relics of galaxy collisions, locked in orbits that tightened over billions of years. Each collision leaves a unique fingerprint in the waves, clues to the black hole's origins and the history of the universe itself. But the real magic happens when gravitational waves team up with traditional telescopes. In 2017, LIGO detected ripples from 2 neutron stars colliding, a cataclysm so powerful it forged heavy elements like gold and platinum. Within hours, telescopes worldwide spotted the glowing aftermath, linking the wave signal to a visible fireworks show. This marked the dawn of multi-messenger astronomy, where we observe cosmic events through both light and space-time vibrations, like seeing and hearing a storm approach from different directions. Yet the most thrilling discoveries might still lie ahead. Future detectors, like the space-based LISA mission, could catch waves from supermassive black holes merging at the hearts of galaxies, events so powerful they drown out all other signals in the universe. Others might reveal primordial waves from cosmic inflation, whispers from the universe's first moments. With each new detection, we're not just learning about black holes or neutron stars, we're decoding the hidden symphony of space-time, a language that's been murmuring to us since the dawn of time. For centuries, black holes existed only in equations and imagination until April 10, 2019, when humanity stared directly into the abyss for the first time. The Event Horizon Telescope, a planet-sized array of observatories spanning the globe, unveiled an image that made history: a fiery orange ring encircling a perfect circle of darkness. This wasn't an artist's rendering or a simulation. It was the shadow of supermassive black hole M87, a monster 55 million light-years away, finally revealed in stark reality. What makes this image so extraordinary isn't just the achievement, it's what the shadow actually represents. That dark center isn't the black hole itself. It's the absence of light escaping from a region roughly 2.5 times larger than the event horizon, warped by gravity into a perfect circle. The glowing ring, that superheated plasma swirling at near light speeds, bent into a halo by the black hole's gravitational lensing. It's as if space-time itself has become a funhouse mirror, twisting the light from behind the black hole into a complete loop visible from Earth. The scale of this accomplishment is hard to overstate. Capturing this image required synchronizing 8 radio telescopes across 4 continents, from the icy peaks of the South Pole to the volcanic slopes of Hawaii. Together, they formed a virtual telescope as wide as Earth itself, a feat akin to reading a newspaper in New York from a sidewalk cafe in Paris. The data gathered in just a few nights of observation was so vast it couldn't be sent over the internet. Hard drives had to be physically flown to supercomputers for processing. But the real magic lies in what this shadow teaches us. The near-perfect circular shape confirmed Einstein's predictions about how black holes warp spacetime with eerie precision. The size of the shadow allowed scientists to calculate M87's mass with unprecedented accuracy, 6.5 billion times that of our Sun. Even the asymmetry in the ring's brightness hinted at the black hole's spin, revealing how it drags spacetime around it like a cosmic whirlpool. Yet for all it revealed, the image also deepened the mystery. Why is the brightness in the ring so uneven? Could there be hidden structures in the turbulent plasma, or does the black hole's magnetic field play a larger role than we thought? And what about the jet, visible in wider observations but conspicuously absent from the iconic image? These aren't just technical details, they're clues about how black holes feed, grow, and shape their galaxies. The Event Horizon Telescope didn't just give us a picture, it opened a new era of astronomy. Future observations, with even more telescopes added to the array, promise sharper images and maybe even movies of black holes in action. Imagine watching the shadow wobble as the black hole consumes a star, or seeing the ring flicker as magnetic fields snap and reconnect. This isn't science fiction anymore. It's the next chapter in our quest to understand the most enigmatic objects in the universe, not as abstract equations, but as real, dynamic monsters casting shadows across the cosmos. The fabric of spacetime seems smooth and unbroken when we look at the vast cosmos, planets orbiting stars, galaxies swirling through the void, but zoom in far enough and this serene picture shatters. At scales 1 trillion times smaller than an atom, spacetime itself might churn like a stormy ocean, bubbling with fleeting particles and energy fluctuations. This is quantum foam, a dizzying concept where the very stage of reality becomes unpredictable, popping in and out of existence in a chaotic dance governed by quantum mechanics. Picture tossing a stone into a placid pond. The ripples spread smoothly across the surface. Now imagine that same pond constantly boiling, with tiny bubbles forming and vanishing too quickly to see. Quantum foam suggests spacetime behaves like that second pond, except instead of water, it's the fabric of the universe itself that's frothing. These aren't just mathematical abstractions, they're potential windows into how gravity and quantum mechanics might finally shake hands. Near a black hole's singularity, where gravity reaches infinite strength, this foam could become the dominant feature of reality, turning the orderly rules of physics into a frenzied quantum free-for-all. What's wild is that this idea isn't pure speculation. The seeds of quantum foam were planted by physicist John Wheeler in the 1950s. who realized that at the tiniest scales, Heisenberg's uncertainty principle would prevent spacetime from remaining smooth. Energy fluctuations would create microscopic black holes and wormholes, blinking in and out of existence so fast they'd be nearly impossible to detect. It's as if the universe has a hidden layer of turbulence, normally invisible but waiting to surface under extreme conditions, like near a singularity, where gravity twists spacetime to its breaking point. The implications are staggering. If quantum foam exists, it could mean that at fundamental levels, spacetime isn't continuous but granular, like a digital image that appears smooth until you zoom in and see the pixels. Some theories, like loop quantum gravity, take this further, proposing that space is woven from tiny, indivisible loops. Others suggest the foam could contain wormholes or even baby universes, constantly sprouting and collapsing like bubbles in a cosmic soda. But here's the catch: we've never directly observed it. Quantum foam operates at scales so small and durations so brief that current technology can't probe it. Yet black holes might be the key to unlocking this mystery. Near a singularity where gravity warps spacetime beyond recognition, quantum effects could amplify, making the foam's turbulence impossible to ignore. Some models even suggest that instead of a sharp, infinitely dense point, a black hole's core might be a seething ball of quantum foam, a place where space and time lose all meaning, replaced by probabilities and fluctuations. It's a radical departure from the smooth, predictable universe we're used to, but it might be the only way to avoid the nonsensical infinities that plague classical physics at the singularity. This isn't just about black holes, it's about the nature of reality itself. If spacetime is frothy at its core, it could rewrite our understanding of everything from the Big Bang to the future of the cosmos. Maybe the universe began as a quantum fluctuation in some larger foam, or perhaps dark energy's mysterious push is linked to this hidden turbulence. For now, quantum foam remains one of the most tantalizing what-ifs in physics, a reminder that the universe's deepest secrets might be hiding in the spaces between the smallest things we can imagine. What if black holes aren't the smooth, empty voids we imagine? What if, instead of a crushing singularity at their core, they're filled with a frenzied tangle of cosmic strings vibrating at the universe's most fundamental level? This isn't science fiction, it's the radical Fuzzball hypothesis emerging from string theory, and it could solve some of the most stubborn paradoxes haunting black hole physics. At the heart of this idea is a simple but profound shift in perspective. Traditional black hole models hit a wall at the singularity, a point where gravity becomes infinite and our equations break down. But string theory, which posits that particles are actually tiny, vibrating strings, offers an alternative. Instead of collapsing into a dimensionless dot, a black hole might be a fuzzball, a dense, stringy mess stretching all the way to its event horizon. Picture a ball of yarn magnified to cosmic scales, where each thread is a vibrating string humming with energy, and you're close to the vision physicists like Samir Mathur have proposed. Why does this matter? For starters, fuzzballs erase the need for a singularity altogether. No infinite density, no breakdown of physics, just a chaotic but finite knot of strings obeying the universe's quantum rules. This could resolve the infamous black hole information paradox, the puzzle over whether information swallowed by a black hole is truly lost. In the fuzzball model, information isn't destroyed. It's encoded in the vibrations of the strings, like a cosmic symphony where every note is preserved. The implications ripple outward. If black holes are fuzzballs, their event horizons might not be the quiet, empty gateways we thought. Instead, they could be dynamic surfaces bristling with stringy activity. This would explain why Hawking radiation carries information, a problem that stumped physicists for decades. The strings near the surface could subtly imprint data onto escaping particles, like whispers passed through a prison wall. But the real magic lies in how fuzzballs bridge the gap between gravity and quantum mechanics. String theory's promise has always been its ability to unify these two pillars of physics, and fuzzballs could be the missing link. By replacing the singularity with a quantum object, they offer a playground where both theories work in harmony, without the infinities that plague classical black hole models. Of course, not everyone's convinced. Critics point out that string theory itself remains untested, and fuzzballs are even further from direct observation. How do you probe something hidden behind an event horizon? Some physicists argue that without experimental proof, fuzzballs are just elegant math, a beautiful idea without a way to verify it. Yet supporters counter that the same was once said about black holes themselves, and look where we are now, snapping photos of their shadows. Whether fuzzballs are real or not, they've already done something remarkable. They've stretched our imagination. They remind us that the universe's strangest corners might not play by the rules we're used to, and that even the most established ideas, like the singularity, might be placeholders for something wilder. As we peer deeper into the abyss, who knows what other surprises are waiting, tangled in the strings of reality itself. Imagine approaching a black hole's event horizon, expecting to cross silently into oblivion, only to hit a searing wall of energy so intense it vaporizes you instantly. This isn't a scene from a sci-fi horror story. It's the startling Firewall Hypothesis, a theory that set physics ablaze with controversy. At first glance, the idea seems outrageous. Einstein's general relativity describes the event horizon as an unremarkable boundary, a point where space flows inward smoothly, like a river slipping over a waterfall. But when quantum mechanics enters the picture, the horizon transforms into something far more violent. According to some interpretations, it could be a literal firewall, a blistering barrier of high-energy particles waiting to obliterate anything daring enough to approach. The firewall puzzle stems from a cosmic game of telephone between quantum mechanics and gravity. When matter falls toward a black hole, quantum theory insists that the information it carries can't just vanish. But how? One possibility is that the energy required to preserve this information gets concentrated at the horizon, creating a scorching layer of radiation. Picture it like a cosmic shredder. Instead of slipping quietly into the black hole, incoming particles collide with outgoing Hawking radiation at energies so extreme they spark a fiery annihilation. The result, a boundary that's less like a gentle threshold and more like the surface of a star, blazing at temperatures hotter than the core of a supernova. This idea doesn't just challenge textbooks, it upends them. If firewalls exist, the smooth spacetime Einstein described near the horizon would be an illusion. Instead of a free-falling observer feeling nothing unusual, they'd be reduced to ash in an instant. That contradicts the foundational principle of equivalence, which states that free fall should feel indistinguishable from floating in empty space. It's like jumping off a ladder and expecting to float, only to slam into an invisible floor halfway down. The implications are so jarring that even the theorists who proposed firewalls admit they're a last resort, a desperate solution to the information paradox that might hint at deeper flaws in our understanding of physics. Yet the firewall hypothesis isn't just a problem, it's a provocation. It forces physicists to confront the messy intersection of quantum mechanics and gravity head-on. If spacetime can't remain smooth at the horizon, what does that say about its fundamental nature? Could spacetime itself be emergent, like the surface of a pond that seems smooth until you zoom in and see the ripples? Some researchers argue firewalls are a sign that we're missing a crucial piece of the puzzle, perhaps a theory of quantum gravity that reconciles these two warring frameworks. Others suggest the paradox might dissolve if black holes are fuzzballs or if information escapes through hidden wormholes. The debate rages on with no clear winner yet. But that's the beauty of it. Firewalls, whether real or not, have ignited a revolution in how we think about black holes. They remind us that the universe's most extreme environments don't just test our theories. They break them, forcing us to invent new rules. And somewhere in that collision of ideas, between the flames of the firewall and the calm of Einstein's spacetime, we might just find the spark that lights the way to a deeper truth. Black holes aren't just silent predators, they might be whispering secrets in ways we're only beginning to hear. Astronomers have recently detected strange, repeating signals near black holes that shouldn't exist according to classical physics. These faint echoes, picked up in gravitational wave data and X-ray observations, ripple outward like cosmic sonar, hinting at something extraordinary happening just beyond the event horizon. Picture shouting into a canyon and hearing your voice bounce back, except here, the canyon is a black hole, and the echoes might be carrying clues about the very fabric of space-time. What makes these echoes so puzzling is their timing. When matter spirals into a black hole, it's supposed to vanish without a trace, no rebound, no second act. But these signals repeat at regular intervals like a cosmic heartbeat, suggesting that some energy or information isn't being swallowed but reflected. One radical explanation points to quantum mechanics. Near the event horizon, particles popping in and out of existence could create a sort of quantum wall, bouncing some radiation back outward. It's as if the black hole's edge isn't perfectly smooth but textured, like a frosted window scattering light in unexpected directions. Another possibility is even wilder. The echoes might be evidence of exotic structures like Planck stars or wormholes lurking just inside the event horizon. These theoretical objects, predicted by some quantum gravity models, could act like cosmic mirrors, catching radiation and flinging it back into space before it's lost forever. Imagine a black hole not as a bottomless pit, but as a dense, compact object wrapped in a gravitational veil, its true surface hidden just beneath the horizon, deflecting signals we're only now learning to decode. The stakes couldn't be higher. If these echoes are real, they could upend our understanding of black holes as simple gravitational traps. Instead, they might be dynamic, layered objects with complex interiors, cosmic onions peeling back to reveal new physics. Some researchers even speculate that the echoes could carry imprints of what fell in, like a faint holographic recording etched into the radiation. It's a tantalizing thought. Black holes might not be the universe's shredders after all, but its archivists preserving information in ways we're just starting to glimpse. Yet skepticism remains. Detecting these echoes is like listening for a whisper in a hurricane. The signals are faint, and interference from surrounding matter or instrument noise could muddy the results. Teams analyzing the same data sometimes disagree, with some claiming groundbreaking discoveries and others dismissing them as statistical flukes. The debate is healthy, even exhilarating, because it pushes astronomers to refine their tools and theories, sharpening our ability to interrogate the cosmos. What's undeniable is how these echoes capture the imagination. They remind us that black holes, for all their terrifying power, might still hide surprises, subtle, shimmering hints that the universe is stranger than we dreamed. Whether they're quantum graffiti, hidden structures, or something entirely unforeseen, each echo is a ripple in the dark, inviting us to lean closer and listen. And in that listening, we might just hear the future of physics being written. Black holes might seem like the ultimate destroyers of order, but they hide a secret: they're actually masters of chaos. And not just any chaos, but a precise, measurable kind encoded in a property called entropy. In everyday life, entropy describes disorder. Think of a messy room or melting ice cream. But for black holes, entropy isn't about clutter. It's about information. Every particle, every atom that falls into a black hole leaves a ghostly imprint on its event horizon, scrambled into a quantum code so complex it defies imagination. The mind-blowing part: the entropy of a black hole isn't proportional to its volume, like you'd expect, but to the area of its event horizon. It's as if the universe is telling us that the true nature of reality isn't three-dimensional but something far stranger, a cosmic hologram where the surface holds the keys to the interior. This revelation came from physicist Jacob Bekenstein in the 1970s, who dared to ask, if black holes follow the laws of thermodynamics, shouldn't they have entropy too? The idea was radical. Entropy had always been tied to heat and molecular motion, not gravity. But Bekenstein's calculations showed that a black hole's entropy is colossal, far greater than any ordinary object of the same size. Take a black hole with the mass of our Sun. Its entropy would be a number so large it dwarfs the combined entropy of every particle in the observable universe. That's not just a quirk, it's a clue that black holes are the ultimate information processors, storing data in ways we're only beginning to grasp. The math behind this is elegant yet profound. Bekenstein and Hawking discovered that a black hole's entropy equals 1/4 of its event horizon's area, measured in Planck units, the smallest possible pieces of space. This simple formula bridges two seemingly unrelated worlds, gravity and quantum mechanics. It suggests that the event horizon isn't just a boundary but a buzzing, dynamic surface where quantum bits of information dance in patterns we can't yet decode. Think of it like a hard drive with unimaginable storage capacity, where every square Planck length holds a binary digit of cosmic data. But why does this matter? Because black hole entropy isn't just a number, it's a Rosetta Stone for physics. It hints that space-time itself might be emergent, like the surface of a pond whose waves only look like separate ripples. If the universe's deepest truths are written not in volumes but on surfaces, then black holes are the ultimate scribes, encoding secrets in their event horizons. This idea, called the holographic principle, turns our intuition inside out. Reality as we experience it might just be a projection, a 3D movie playing on a 2D screen at the edge of the cosmos. The implications ripple outward. If black holes have entropy, they must also have temperature, a fact Hawking proved when he discovered black holes radiate heat. This tiny glow, now called Hawking radiation, is the universe's way of balancing the books, ensuring that even the darkest objects obey thermodynamics. But here's the twist: as a black hole loses mass through radiation, its event horizon shrinks, reducing its entropy. That seems to violate the second law of thermodynamics, which says entropy always increases. The resolution, the radiation itself, carries away the missing entropy, like a thief leaving fingerprints at the scene. It's a cosmic shell game where information is never truly lost, just scrambled beyond recognition. This dance between entropy, information, and gravity is more than theoretical gymnastics. It's a roadmap to the next great revolution in physics. Black holes challenge us to rethink everything, from the nature of space and time to the fate of information in the universe. They're not just celestial oddities, they're teachers, showing us that chaos and order might be two sides of the same coin, and that the universe's deepest truths are written in the language of entropy, waiting for us to decipher them. Black holes seem almost disappointingly simple at first glance. According to the No-Hair Theorem, these cosmic monsters can be completely described by just three properties: their mass, electric charge, and spin. No frills, no extra details, no messy complications. It's as if the universe took one of its most complex objects and stripped it down to its bare essentials, like a sculptor carving away everything unnecessary to reveal the purest form beneath. But here's the twist. This elegant simplicity might be an illusion, a cosmic sleight of hand hiding a far richer reality. Think of it like meeting someone who only tells you their height, weight, and favorite color. You'd know basic facts about them, but nothing about their personality, history, or dreams. The No-Hair Theorem reduces black holes to a similar skeletal description, ignoring everything that fell into them. Stars, planets, even entire civilizations could vanish beyond the event horizon, and from the outside, the black hole would look exactly the same, just a bit heavier, maybe with a slight change in spin or charge. It's as if the universe has a strict no-refunds policy for information, sealing it away behind a curtain of gravity. But does this really hold up? Recent research suggests black holes might be far more complex than the No-Hair Theorem allows. Take gravitational waves, for example. When two black holes collide, the ripples in spacetime they produce carry subtle fingerprints, tiny deviations from perfect smoothness that could hint at hidden structures near the event horizon. Some physicists argue these hairs might encode details about the black hole's history, like scars from past mergers or imprints of the matter it's consumed. It's as if black holes aren't just bald spheres but might have faint, quantum hairstyles too fine for our current tools to detect. Then there's the holographic principle, which suggests all the information swallowed by a black hole isn't lost but smeared across its event horizon like data on a cosmic hard drive. If true, the No-Hair Theorem's simplicity is just a surface-level trick, a smooth facade over a seething quantum underbelly. Imagine a locked book. From the outside, you only see the cover: mass, spin, charge, but inside, every page is filled with intricate text. The challenge: peeking inside without opening the book, or in this case, crossing the event horizon. The debate gets even wilder when quantum mechanics enters the picture. According to quantum theory, information can't be destroyed. Yet the No-Hair Theorem seems to suggest it vanishes without a trace inside a black hole. This contradiction has led some theorists to propose radical alternatives, like fuzzballs or firewalls, where the event horizon isn't smooth but bristling with quantum activity. These ideas challenge the No-Hair Theorem's core assumption, painting black holes as dynamic, complex objects with hidden layers waiting to be decoded. So is the No-Hair Theorem wrong? Not necessarily, but it might be incomplete. Like Newton's laws before Einstein, it could be a brilliant approximation that breaks down under extreme conditions. Future telescopes, gravitational wave detectors, or even quantum experiments might one day reveal the hairs hiding in plain sight, proving that black holes are far more than their mass, spin, and charge. Until then, this cosmic barbershop debate remains one of the most thrilling frontiers in physics, a reminder that even the simplest objects in the universe might be keeping secrets. The idea that black holes might be cosmic backdoors, gateways to entirely new universes with different laws of physics sounds like pure science fiction. Yet some of the most respected theories in cosmology suggest this wild possibility isn't just fantasy. Imagine a black hole not as a dead end, but as a cosmic seed, birthing a new space-time bubble with its own unique rules. This isn't just speculation, it's a hypothesis grounded in the mind-bending math of quantum gravity and inflationary cosmology. Take the concept of bubble universes. According to some models of eternal inflation, Our universe might be one of countless others, each born from quantum fluctuations in an ever-expanding multiverse. Now picture a black hole singularity, a point where space-time curvature becomes infinite. Under these extreme conditions, the fabric of reality could snap and rebound, not into nothingness, but into a new, self-contained universe. It's like blowing a soap bubble inside another bubble. The black hole's collapse might create a separate space-time realm, forever disconnected from our own except through the narrow tunnel of its birth. String theory adds another layer to this idea. In certain interpretations, black holes could be knots of higher dimensional space, their singularities unraveling into entirely new dimensions. Picture a straw. From the side, it looks like a line, but from the end, you see it's a circle. Similarly, a black hole's interior might open up into a hidden dimension, becoming the Big Bang of another universe. The equations even suggest these daughter universes could inherit tweaked versions of our physical constants, slightly different strengths of gravity, altered masses for particles, or even extra dimensions of space. But here's where it gets stranger. These newborn universes wouldn't just be random copies. Some theories propose they'd carry echoes of their parent black hole's properties. The spin, charge, or mass of the original black hole might imprint on the new universe's fundamental laws, like a cosmic DNA passed through the singularity. This could explain why our universe seems so finely tuned for life. If countless variations exist in the multiverse, we simply inhabit one where the numbers lined up right. Of course, not all physicists are convinced. Critics argue that without observable evidence, these ideas remain in the realm of metaphysics. How could we ever detect a universe born from a black hole if it's causally severed from our own? Others point out that even if bubble universes exist, the process might be so rare or unstable that it's effectively irrelevant to our understanding of reality. Yet the allure persists. Black holes as cosmic creators offer a poetic symmetry. The ultimate destroyers might also be the ultimate givers, recycling space-time into new beginnings. Whether they're gateways, seeds, or something beyond our current imagination, one thing's clear: black holes continue to defy our expectations, challenging us to think bigger about where the universe begins and ends. For decades, astronomers have been piecing together a cosmic mystery. 85% of the universe's matter seems to be missing. This invisible stuff, called dark matter, doesn't emit or reflect light, yet its gravitational pull shapes galaxies and bends the fabric of spacetime itself. Scientists have searched for exotic particles to explain it, from WIMP to actions. But what if the answer isn't something new? What if dark matter has been hiding in plain sight, disguised as countless ancient black holes scattered across the cosmos? The idea isn't as far-fetched as it sounds. Primordial black holes, theorized to have formed in the universe's first chaotic seconds, could be the perfect dark matter candidates. Unlike stellar black holes born from dying stars, these relics would have emerged from density fluctuations in the seething soup of the early universe, some as small as asteroids, others as massive as planets. Their sheer numbers could explain dark matter's gravitational effects without requiring undiscovered particles. Picture an invisible swarm of these ancient objects drifting between stars, their collective gravity binding galaxies together like unseen scaffolding. But why haven't we found them yet? Primordial black holes are notoriously elusive. Too small to detect through light, too sparse to spot through lensing effects. They're cosmic ghosts, leaving only faint gravitational ripples as evidence. Some researchers have turned to ingenious methods to hunt them, like monitoring stars for sudden brightening, which could signal a tiny black hole passing in front and magnifying the star's light like a lens. Others scour the cosmos for unexpected gamma-ray bursts, which might betray the explosive death of a primordial black hole evaporating via Hawking radiation. The stakes are high. If even a fraction of dark matter is made of these primordial relics, it would rewrite our understanding of the universe's infancy. Their existence could hint at exotic physics in the moments after the Big Bang, like phase transitions or extra dimensions imprinting their signatures on spacetime. Some theories even suggest these black holes could have seeded the supermassive monsters we see at galactic centers today, growing over billions of years like cosmic snowballs. Yet the puzzle is far from solved. Observations so far have placed tight constraints on how much dark matter primordial black holes could realistically account for. Too many small ones would have disrupted the cosmic microwave background. Too many large ones would have warped the light from distant quasars in ways we don't see. The window where they could exist as dark matter is narrow but not closed. What makes this hunt so thrilling is how it forces us to rethink the boundaries of possibility. Dark matter might not be a single answer but a mix of solutions, primordial black holes dancing alongside yet undiscovered particles. Or perhaps in the universe's infinite creativity, the truth is something stranger still, waiting in the shadows for us to uncover. Either way, the search reminds us that sometimes the most profound secrets aren't hidden in the distant cosmos, but in the overlooked corners of theories we thought we knew. Long before the first black holes formed in the way we understand them today, the universe might have incubated something even stranger: black hole stars. Imagine a star so massive, so radiant, that it could outshine entire galaxies, yet hiding a dark secret at its heart. These theoretical giants, stretching hundreds of times wider than our sun, wouldn't just burn with nuclear fusion, they'd contain a fledgling black hole nestled in their cores, growing steadily as it fed on the star's own flesh. The concept flips stellar evolution on its head. Normally, a massive star lives by fusing elements in its core until it runs out of fuel and collapses into a black hole. But in the early universe, conditions were so extreme that some stars might have skipped this orderly process entirely. Picture a newborn star forming from pristine hydrogen and helium, untouched by heavier elements. If it grew large enough, hundreds of thousands or even millions of solar masses, its core could become so dense and hot that quantum fluctuations would trigger a black hole's birth while the star was still shining. Instead of dying in a supernova, this star would become a cosmic hybrid, its outer layers blazing with fusion while its core quietly transformed into an insatiable gravitational pit. What's truly wild is how these stars could solve one of cosmology's biggest puzzles: the existence of supermassive black holes in the early universe. Astronomers have spotted quasars, bright disks of matter swirling around billion solar mass black holes, shining from when the cosmos was less than 1 billion years old. That's not enough time for ordinary black holes to grow so large through mergers or accretion. But a black hole star, it could act like a cosmic incubator, feeding its dark heart for millions of years before the star's outer layers finally gave way. The result, a ready-made supermassive black hole, far sooner than conventional models allow. The physics behind these stars is as beautiful as it is bizarre. Normally, a black hole's gravity would rip apart anything trying to form around it. But in a black hole star, the outward pressure from fusion in the outer layers balances the inward pull of the core's gravity. It's like a cosmic tug of war where both sides are evenly matched, creating a stable, if surreal, equilibrium. The black hole would grow slowly, consuming material from the star's interior, while the star itself would shine with a strange, steady light, not from fusion alone, but from the intense heat generated by matter spiraling into the core. Some calculations suggest these stars could glow with a peculiar blue hue, colder than expected for their size but far more luminous than any ordinary star. Yet for all their theoretical elegance, black hole stars remain ghosts in the equations. No one has ever observed one, and the conditions needed to form them, a universe free of heavier elements, with vast clouds of pure hydrogen and helium, vanished billions of years ago. But that doesn't mean they're lost to history. If they existed, their remnants might still be with us, lurking at the centers of galaxies as the supermassive black holes we see today. And their legacy could be written in the patterns of ancient light, subtle signatures waiting to be uncovered in the farthest reaches of our telescope's gaze. What's thrilling is how these cosmic oddities challenge our assumptions. They remind us that the universe's early chapters might have been far stranger than we've dared to imagine, with laws of physics pushed to extremes we'll never see again. Whether black hole stars are real or just a brilliant thought experiment, they prove one thing. When it comes to the cosmos, the line between science and speculation is always thinner than we think. Simulating a black hole isn't about creating Hollywood special effects. It's one of the most demanding challenges in modern science. Imagine trying to recreate an environment where gravity is so strong it warps time, where matter moves at nearly the speed of light, and where the laws of physics as we know them break down. This isn't just a math problem, it's a full-scale assault on the limits of computing power. Yet around the world, teams of physicists are doing exactly that, using supercomputers as their digital laboratories to peer into the heart of darkness. Take the simulations run by NASA's Goddard Space Flight Center or the Event Horizon Telescope collaboration. These aren't simple animations, they're precision-crafted virtual experiments, crunching Einstein's equations across billions of data points to model how black holes bend light, shred stars, or collide in cataclysmic mergers. One of the most striking simulations revealed what happens when two supermassive black holes spiral toward each other. The result, spacetime itself twists into intricate patterns, sending out gravitational waves like ripples from a stone dropped in a pond. These simulations didn't just look stunning, they helped scientists interpret real-world observations, like the signals picked up by LIGO when black holes collide billions of light years away. But why go to such lengths? Because black holes refuse to play by ordinary rules. Near the event horizon, matter doesn't behave like gas or plasma. It becomes a superheated, magnetized chaos, with particles accelerated to energies far beyond anything we can create in particle colliders. Supercomputers like Summit at Oak Ridge National Laboratory or Fugaku in Japan divide this chaos into manageable chunks, simulating tiny slices of spacetime where magnetic fields snap and reconnect, where turbulence spawns whirlpools of plasma, and where gravity's grip distorts light into surreal rings. It's like rebuilding a hurricane atom by atom, then watching it unfold in slow motion. What's truly groundbreaking is how these simulations bridge theory and reality. Before the first image of a black hole's shadow was captured in 2019, scientists ran thousands of simulations to predict what it might look like. They tweaked variables, spin rate, accretion disk thickness, magnetic field strength, generating a library of possible outcomes. When the real image matched one of their models, it wasn't just a victory for Einstein's theories. It validated the entire approach of using supercomputers as cosmic crystal balls. Now, the same techniques are being used to probe even wilder questions, like what happens inside a black hole's event horizon, or how wormholes might behave if they exist. Yet for all their power, these simulations have limits. Even the fastest supercomputers can't perfectly replicate quantum effects near a singularity or model every atom in a swirling accretion disk. That's where ingenuity comes in. Researchers use clever shortcuts like adaptive mesh refinement, focusing computing power only on the most critical regions, or machine learning to predict how small-scale physics influences the bigger picture. It's a bit like painting a masterpiece with only a handful of brushstrokes carefully chosen to suggest the rest. The future of black hole simulations is even more thrilling. Exascale computing, the next frontier, will allow models with unprecedented detail, perhaps even revealing how black holes spark the jets that pierce galaxies. Others aim to simulate quantum gravity effects, venturing into realms where today's physics falls silent. Every line of code, every calculation, brings us closer to answering the universe's most persistent question: what truly lies beyond the event horizon? Until we can send probes into the abyss, these digital experiments are our best maps to the unknown, a reminder that sometimes to explore the cosmos, you don't need a spaceship. Just a supercomputer and a limitless imagination. Black holes don't just bend space-time, they warp the boundaries of human understanding, forcing us to confront questions that straddle the line between science and philosophy. What happens to the essence of something or someone that crosses the event horizon? Is it obliterated, transformed, or preserved in some unknowable way? These aren't just technical puzzles, they're profound ethical dilemmas. If a black hole destroys information irretrievably, as Hawking once suggested, it challenges the principle that knowledge is fundamental to the universe's structure. But if information escapes, as holographic theories propose, it hints at a cosmos where nothing is ever truly lost, just rewritten in a language we're still learning to read. Consider the sheer scale of a black hole's power. It reduces stars to rubble, twists light into submission, and warps time itself. Yet despite their destructive might, black holes also sculpt the cosmos. They regulate galaxy growth, forge heavy elements in their jets, and might even seed new universes. This duality, destroyer and creator, mirrors ancient myths of cosmic cycles where death feeds new life. It's as if the universe encoded a paradox in these objects. To build, sometimes you must first unravel. Then there's the existential vertigo they induce. A black hole singularity, where physics fails, is a stark reminder of how little we truly know. For all our equations and telescopes, we're peering into an abyss that defies intuition. Some philosophers argue this humility is black holes' greatest gift. They puncture the illusion that reality must conform to human logic, revealing a universe far stranger, far more inventive than our minds can grasp. And what of our place in all this? Black holes underscore how fleeting and fragile human existence is against cosmic time. A supermassive black hole can outlive stars by trillions of years, persisting long after the last light flickers out. Yet here we are, tiny and temporary, decoding their secrets. There's poetry in that, a species born from stardust, daring to unravel the mysteries of the darkest things in existence. Perhaps the most haunting question isn't about black holes at all, but about us. If the universe can create phenomena so alien, so beyond our experience, what else lies beyond the edges of our imagination? Every answer we claw from the darkness seems to reveal deeper layers of mystery, and maybe that's the point. Black holes aren't just objects, they're mirrors reflecting back our boundless curiosity and our eternal hunger to find meaning in the void. The quest to unravel black hole mysteries is far from over. In fact, we're standing on the brink of a new golden age of discovery. Imagine telescopes so powerful they could trace the fiery orbits of stars skimming just above an event horizon, or detectors sensitive enough to catch the faintest whispers of quantum foam at a singularity's edge. This isn't science fiction, it's the near future. Projects like the European Space Agency's LISA mission, set to launch in the 2030s, will deploy a trio of spacecraft to hunt gravitational waves from supermassive black hole mergers with precision never before possible. Unlike ground-based observatories, LISA space-borne detectors will bypass Earth's noise, tuning into cosmic ripples at frequencies too low for current instruments to hear, revealing collisions of black holes so massive they shake spacetime itself. But gravitational waves are just the beginning. Next-generation telescopes like the Vera-C, Rubin Observatory, and the extremely large telescope ELT will peer deeper into galactic cores, capturing real-time movies of matter swirling into black holes. The ELT's 39-meter mirror, nearly half the length of a football field, will collect enough light to spot stars wobbling under the grip of intermediate mass black holes, the elusive, missing link between stellar remnants and supermassive giants. Meanwhile, the James Webb Space Telescope's infrared eyes are already uncovering quasars from the universe's infancy, probing how black holes grew so vast so quickly. These tools aren't just upgrading our vision, they're rewriting the playbook on cosmic evolution. On the theoretical front, quantum gravity experiments are inching closer to testing ideas once deemed untouchable. Lab-based simulations using ultra-cold atoms or holographic quantum systems aim to recreate conditions near an event horizon, offering glimpses of how spacetime might behave under extreme quantum strain. Some physicists are even exploring analog black holes in materials like graphene, where electron behavior mimics relativity's rules. These tabletop experiments won't replace astrophysical observations, but they could crack open questions about information loss, firewalls, or whether singularities truly exist, problems that have stumped physicists for decades. Perhaps most tantalizing are the wildcards technologies we can't yet imagine. Just as the laser revolutionized astronomy decades after its invention, breakthroughs in quantum computing or AI-driven data analysis might uncover patterns in black hole data invisible to human eyes. Already, machine learning is sifting through telescope archives, flagging oddities like orphaned jets or quiet quasars that defy textbook models. The next Einstein or Hawking might not be staring through a telescope, but training an algorithm to spot the universe's best-kept secrets. What ties these threads together is a single, thrilling truth. Black holes are no longer static riddles. They're dynamic puzzles, yielding new pieces with every technological leap. Whether it's catching the glow of a primordial black hole's final evaporation, decoding holographic echoes from an event horizon, or stumbling upon a wormhole's telltale signature in gravitational waves, the coming decades promise something far better than answers. They'll deliver better questions. And in that endless cycle of curiosity and discovery, we're not just observers, we're participants shaping the story of how the universe reveals itself, one black hole at a time. As we peer into the abyss, black holes remind us of the universe's boundless mysteries, not just as cosmic oddities, but as mirrors reflecting the limits of human knowledge. Every breakthrough, from Hawking radiation to the first image of an event horizon, peels back another layer of the unknown, revealing just how much we've yet to learn. These gravitational enigmas defy intuition, blending the familiar laws of physics with quantum riddles that still leave scientists wide-eyed. They're more than celestial objects, they're classrooms where spacetime itself teaches us humility and wonder. Consider how far we've come. A century ago, black holes were mere scribbles in Einstein's equations, mathematical curiosities dismissed as too bizarre to exist. Today, we've not only proven their reality but captured their shadows, heard their collisions through gravitational waves, and even theorized their potential to birth new universes. Yet with each answer, new questions erupt like starbursts. What truly happens at the singularity? Is information preserved or lost? Could black holes be gateways, holograms, or something beyond our current imagination? The puzzles pile up, but that's the thrill of exploration. The universe doesn't surrender its secrets easily. What's most exhilarating is realizing we're living through this revolution in real time. The tools now at our fingertips, AI-driven telescopes, quantum simulations, space-based gravitational wave detectors, are turning sci-fi dreams into scientific routine. Who's to say what the next decade will reveal? Perhaps a high school student watching this right now will one day crack the code of quantum gravity, or an amateur astronomer will spot the telltale flicker of a primordial black hole. The frontier is wide open, and the next great discovery could come from anywhere. So while black holes may seem like distant, indifferent monsters, they've become something deeply human, a call to curiosity. They remind us that the cosmos isn't just stranger than we imagine, it's stranger than we can imagine, and that's the real gift of these dark wonders. They don't just warp space-time, they stretch our minds, pushing us to think bigger, question deeper, and embrace the joy of not knowing. The story of black holes is still being written, and somewhere in its next chapter, there might be a revelation waiting to rewrite everything we thought was true. So keep looking up, stay restless, because the universe's greatest mysteries aren't locked away, they're out there, hidden in plain sight, waiting for someone bold enough to ask the right questions. And who knows, that someone could be you.